Hey, welcome. Are you in a physics or maybe even a chemistry class and you have a tough specific heat capacity or a calorimeter lab type question or assignment? Or in other words, do you have questions like number 1 and number 2 here? What is the specific heat capacity of an unknown metal? Or what is the final temperature of a container of water when a piece of hot metal is added to it? Those are lab questions or harder assignment questions that you might see that deal with specific heat capacity, or if you're in a chem class, it could be called a calorimetry lab. So let's go ahead and talk through it. I'm going to show you how to deal with these in a very straightforward way. So let's go ahead and get to it. First up, if you have the question, how do you solve for the specific heat capacity of an unknown metal, which is a common problem that you might see, you're going to start by thinking, all right, if I put a piece of hot metal into a cup of cool water, kind of like this diagram down below here, this step right here is really important. Remember, they're going to come to thermal equilibrium, and the metal is hot. So it's, over the course of being in contact with the water, it's actually going to lose heat to the water, and the water is going to gain heat. And so we need to signify that with a negative Q value for the metal. That's going to be really important to remember that step. And then we can say, well, based off of what we've done before, I can put a link up into the first screencast I did on this, but we do have an equation here where the amount of heat is equal to the specific heat capacity of the water times the mass of the water times the change in temperature of the water is equal to the negative of the specific heat capacity of the metal times the mass of the metal times the temperature change of the metal. All right, and in terms of our variables, what are we looking for here? If we're looking for the specific heat capacity of the metal, is that Cp, is that an M, is that a T, or a delta T, or a T final, T initial? What do you think that is? Well, it's going to be a Cp, specific heat capacity of the metal itself. So that's our unknown right there, so we want to just isolate for it. So I'm going to divide by what's left over here, both sides of the equation. That will cancel out this and this. And of course, if I do that on the right side, I have to do the same thing on the left side. And then if I isolate for my unknown and bring the negative sign over, meaning I multiply both sides of the equation by a -1, I end up with this, and I'm ready to plug in my numbers and solve for the specific heat capacity of the unknown metal that you put into a cup of room temperature water. This is done in chemistry classes and in physics classes. It's something you may be exposed to as a lab or as a problem in an assignment. All right, let's take a look at the second one. A second less common problem, but still really crucial to understand, is what would be the final equilibrium temperature. So let's say you know what the specific heat capacity of the metal is. You put it into the cup of water, you know how much water you have, you know what the masses of both things are. You want to anticipate what the final temperature is going to be for the system that's in thermal equilibrium here. So the piece of metal and the cup of water over here, if you're using styrofoam cups, they work pretty well as insulators for reasonably short periods of time. So we're going to assume no energy flows in or out of the styrofoam cup. And so we're going to start conceptually by saying, well, we put a hot piece of metal in here into room temperature water. So something must be losing energy, something must be gaining energy. So what is going to be losing energy and what's going to be gaining energy? Well, the metal is going to be losing energy, and it turns out that it's going to lose exactly the same amount of energy that the water gains. And this is, again, a really important step in the whole process, is to make sure you make this negative to say that the metal loses energy and the water is going to be positive, it's going to gain energy. All right, so we can go ahead and substitute in what we know the equation is for specific heat capacity over here, or at least a variation of it. And notice anytime we have a delta, we're talking about a final minus initial over here. So we've got this over here, this over here. So what we're looking for is the final temperature of the water, and we're looking for the final temperature of the metal. And if you're familiar with the concept of thermal equilibrium, if we allow enough time, the temperature of the water and the metal are going to be one and the same. The water temperature is going to raise up and the metal temperature is going to lower until they reach the same internal temperature inside the cup here. So one thing we need to do is tease this out. This is going to get really big in terms of an algebraic equation here. And you have to be very careful to not make a mistake because it's very easy to make a mistake. What I'm going to do is show all of my work on the left side of the equation with an equal sign to the right, and all of my work on the right side of the equation with an equal sign to the left. And all I've done is I have taken this as like a coefficient and distribute it into the TF minus TI. So I've got CPW MW times temperature of the water final minus CPW MW times temperature initial of the water. And I did similar things over here. I just have to remember that I've got a negative sign out in front that has to be distributed in, and we'll do that in most likely our next step. And so notice I have done that in our next step. I'm going to label this as equation 1 so we can see where I got that from. Remember, all I'm doing here is just distributing this negative sign. And we want to solve for the temperature of the water final. So we have that over here, and the temperature of the metal final. That actually turns out that they are going to be the same temperature, right? So we're going to talk about this as a strategy, but rather than having two different variables here, two different unknowns, I should say, we want to have just one unknown. And so I want you to think about, well, if they are the same temperature, could we call them the same thing and go from two unknowns down to one unknown? And the answer is yes. I'm going to show you how to do that in just a second. So let's continue with where we left off. Algebraically first, I'm going to move this term to the right and this term over here to the left. And all I'm doing is trying to isolate for my unknown. I'm going to move my unknowns to the left-hand side and my known values to the right-hand side, generally speaking. So now I've got my unknown over here, my unknown over here, and here's the concept that I just mentioned. Remember, if they are coming to the same temperature, the temperature of the metal final, the final temperature of the metal, and the temperature of the water final, or the final temperature of the water, they are both just the final temperature, right? Like, in other words, this looks like two unknowns. Like we have an unknown here and an unknown here. Why not just call them a more general temperature final? And if we do that, that's going to make it so that we only have one unknown rather than two. And that's what we're going to do in our next step. So this is just the left-hand side. This is all I had room for on this slide. But if you take a look over here, I'm now just calling this temperature final over here and this temperature final. And this is a crucial strategy in physics because many times we have simply too many unknowns. All right, so let's continue. This is going to be the left side. This is the right side of the equation that was unmodified from the previous line. And now I can draw out my unknown. And this is what's left over here, factoring it out. And then I can go ahead and isolate my unknown, and I'm ready to plug in my numbers. So this has a lot of variables, and the algebra is tricky. It's tricky to get right and to not make a little mistake. If you've gotten to this stage in a physics or a chemistry class, you're probably good with algebra, but it's still easy to make a little mistake in this problem that'll throw off the entire thing, which is why I wanted to make a screencast on this so that your work can look like this and so that you can understand how to go about doing this. So hopefully this has been helpful. I'm going to do more screencasts in this unit and for the rest of physics. If you have any comments, please let me know down below, and I hope you all have a great day. Take care.